snowstorm or what have you, you may just want to watch the videos, but otherwise, please try to be here, because this is where a lot of the action happens in terms of learning. Okay? But the videos will be available, and they will continue to be available, through and past the final exam. Okay. Great. So, ladies and gentlemen, we begin our journey with simulation modeling by calling up the software package of Node. And so any of you who are on machines here, or for whatever reason have AnyLogic PLE already installed, please log in as required. And through the Start menu or the Apple menu or through the Linux Applications menu, I'd like you to start up AnyLogic. Okay? And just to make sure we're all having a consistent experience, I will do the same. Now, I'm well aware of the fact that on this first day, not everyone has recourse to such a machine. If you don't, pull up near someone who does. Okay? I will be illustrating all the processes up here on my machine as well. So, yes, question?
It looks like AnyLogic isn't on Linux.
It's not, okay. So it's only on the Windows side, it looks like. I appreciate that, Maverick. So it looks like you'll need to, I will talk to the tech staff about that, because it runs fine, as you will see on Linux. But I will talk with them about seeing if we can get it on there. For now, you'll need to use the Windows side, it sounds like. Okay. So I'm going to call up AnyLogic. AnyLogic is a software package created by the Epinonymous company. It is a package that is particularly advanced in several features, including support for multiple types of simulation modeling, oft supported by different platforms, and the ability to weave those types of modeling together. Okay? It turns out that each of these types of simulation modeling is very well adapted for characterizing certain types of systems in the world. There's an economy of expression in describing systems of certain types with a particular modeling approach. For systems that are feedback rich, evolved accumulation, system dynamics is often bang-on tool. For ones that involve interacting individuals, interacting through networks and spatial context, agent-based modeling. If you're dealing with resource-constrained workflows, etc., discrete event simulation. All of those are supported by this package. Now, have you folks been able, most people been able to call, who are on these machines, been able to call that up? Yeah? Okay. Okay, that always lends me some uncertainty. Do people need more time? That's the operative question. No? Okay.
Yes.
Yes, need more time. Okay. So when AnyLogic comes up, many of you will see this sort of screen. If you've used AnyLogic before, you may see something different, but many of you will see this screen. And this provides you with a wealth of resources, some of which have come out of our lab and university for AnyLogic modeling. But what you will want to do in this case is to minimize the screen. Does anyone recognize this environment? What does this look like to you? Yeah.
Welcome page.
Okay, it's a welcome page, but what environment is this in? I think many of you will have seen it before. It's Eclipse. This is Eclipse, ladies and gentlemen. AnyLogic is an Eclipse plugin, okay? But it's an Eclipse plugin that's customized to a level that it's not just in the marketplace of plugins, and it has limitations and other plugins that you can use. But at the same time, many of the tricks you may have learned with Eclipse in other classes you can use here. And we'll be making use of those tricks on occasion. So I'd like you to minimize this. And what you'll find is many tabs. And your tabs will probably look different than mine because of the vagaries of how I've arranged them in the past. But what we'll broadly see is we'll see several tabs associated with different areas of the modeling workspace. And if we go up here to look at the view menu, you'll find that there's lots of sort of different components we can enable. We can enable a search pane, or a pane that shows us statically detected problems with our model, or a palette out of which we will paint our models. Okay, all of these are components of the AnyLogic software. We're going to be doing something much simpler in this case than building up a model because of the strictures of time and other factors. We're going to be working with a pre-existing model. So I wanted this to be up, but in the meantime, I want you to call up a browser. Okay? Call up a browser, and I'd like you to go to the Moodle site. Maybe you're on the Moodle site already, all the better. Okay? So I'm going to go over here and call up Moodle, and lo and behold, your view will be a bit different than mine because I have the privilege of instructor viewing. But you'll see in the class site here, you may have had to navigate to it through My Courses, 394, 858. You'll see a bunch of different components, including a link to videos for the course, models for use in the course, syllabus, etc. In this case, I'd like you to go to this area that says Models for Use in the Course. Do you see that? Do you see that in Moodle? No? You don't? Okay. The plot thickens. Does anyone see it? Sorry? Oh my gosh. Okay, well the plot thins. Okay, great. Okay, well I'll be. So let's see how we can frob it. Okay. I need to press the eye blocker, and now press the eyeball. Okay. That sounds really uncomfortable. But by pressing the eyeball, it should now be visible. Can you see it now? Okay. Let's engage in frobbing behavior on the other ones as well. Okay. For some reason, that particular one was truculent. The others look like they're visible. Okay. Do you see models for use in class now?
Yeah.
Okay. So I'd like you to go click on, not on the eyeball, but on this model, SIR agent based for PLE. Okay. And when you click on it, according to the Moodle settings that I chose, it should download. Does it download for you?
Yeah.
Okay. Last year we had some issues with people using different browsers. On Safari it did one thing, but it downloads for all of you? Okay, all that are frobbing it? Okay. Okay. So that's going to download what's known as an ALP file to your computer. Okay, an ALP file is an AnyLogic project file, and naturally, being downloaded, it's going to go sit probably in your downloads area. What we're going to do now, having downloaded that file, we're going to go to AnyLogic and open it up. Okay, so AnyLogic's a familiar tool in terms of the general mode of operation. We'll go to File, Open, and find that file and open it up. If it went to your downloads, it'll be in downloads. If it went to your desktop, it'll be in your desktop. Okay. Straightforward thing. Mutatis mutandis. So go here. Here's the software. Do File, Open, and I would like you to find that model whence it comes on your computer. Okay. Now, on my computer, it happens to live in a different place along with hundreds of its peers. So I'm going to go open it up from there. Okay. So File, Open, go find the AnyLogic project model, AnyLogic project file that you downloaded, and it should open it up within AnyLogic. Okay. Okay. Are people encountering any difficulties with those steps that I can comment on? Okay. Okay. So you'll notice when it opens up that this model, this monolithic ALP file, is in fact composed of many subpieces. Now, if you're as geeky as I do, you might want to look at the XML that underlies it. ALP file is actually an XML file. You can sort of read through what's there, but and normally I deal with that through the AnyLogic interface, and you'll see that it's composed of several pieces here. Okay, one of the pieces has to do with a main environment, an environment that sort of provides an overall context for agents to circulate, to engage with one another. But the one I want to drag your attention to is double-click on person and open up the person class. And you should see something like this. Do you see that? Okay. So what this is characterizing is a sort of a theory of personhood with respect to the model, a theory of what it means to be a person, personness, as it were. We characterize the sort of attributes of a person. In this case, they have a singularly simple set of properties, namely color. But it also characterizes them in terms of the processes that they undergo every time. And here, what we see is a state chart. For those with a computer science background, you may have encountered this in 270 state chart, UML state chart. So you still cover this? Yeah. So this is a UML state chart of familiar features from 270 then. And fundamentally, with respect to the concern depicted here, sometimes we'll have multiple state charts for different concerns, but for this particular concern, we characterize a person as being in one of several states. And at any one time, they're either susceptible or they are infectious. In other words, they can transmit an infection, or they are recovered. They're recovered from past exposure. And they've been through the infectious state, and now they're immune to it. Okay? And we see that in addition to having their state characterized into these different possibilities, their current situation being collectively described by those possibilities, which are mutually exclusive and collectively exhaustive. They're in either one or the other of these, and exactly one at a time. Individuals can transition from one to the other. So there's an infection process which will bring someone from susceptible to infectious. There's a recovery process that can bring someone from infectious to recovery. And in fact, there's an immunization process illustrated over here, which can bring someone from susceptible to recovery. And I neglected to name that in an appropriate, transparent fashion. So we have this model depicting not only the states they can be in, but the actions that can lead them to change that from one state to the other. More than that, we have some description of the rules governing those actions. So if we go to recovery, for example, let's go down to this recovery transition, and we engage in clicking behavior with it. We will see that it's defined with a certain rate, and the rate is 1 over the average illness duration. Okay, so they have a certain chance. You could think of it as a chance per day. Indeed, that's a quantity specified in per day terms. A certain kick of the can every day about whether they will recover. And in fact, it's more than that. This is what's called a hazard rate. We'll be talking about it later in class, but it's a continuous chance. Every second they have a certain chance of going that's correspondingly smaller. And that means that that chance is such that they're in this infectious state for a certain average amount of time. Okay? And here, if we go up to infection, what you'll see is that these individuals get infected here by virtue of receiving what's known as a message, which basically reflects a contact. From who do you think might initiate the contact that would infect someone? If I'm a given person, I'm susceptible. What sort of contact would make me become infectious? If I have a contact with whom? Infectious. Yeah, infectious. Someone who's already infectious, right? So we further have a contact process from someone who's infectious, and we can go look at that. That actually doesn't change their state. It simply occurs whilst they're in a state with a certain rate, a hazard rate defined as contact rate. here, and there's some consideration of infection probability per day. And when there's a contact that occurs, they send a message basically indicating, hey, you've been exposed to infection. Okay, so we have these individuals. Each of the individuals has this kind of theory of personhood that's particularly simple and stylized, that boils it down to, okay, they have some infection status and some transitions between states of infection according to certain rules. And as a derivative thing, it turns out they'll have a color as denoted by the colors indicated there. Yellow for susceptible, infectious, sort of this orangish, and recovered gray. Okay, now, this is our theory of personhood. This is kind of a depiction of, as it were, the natural history of infection, the possible states a person can go in their progression. You could think of it as an algorithm of sorts, that under certain conditions does this action, otherwise does those, etc. But these agents are not solitudes. They're not alone. Let's go over here to person, and if we go up to person, what we'll find is there's a large space. It's actually illustrated in this kind of gray area here, where we'll be counting up a number of infectious, susceptible, and recovered people over time. And if you go over and look here in main in the properties window, if you don't see properties, bring it up by view properties. If it's not showing, you can enable it like this. You will see that it's depicting information on the main class. This is the global environment. This is the overall environment. It's the stage in which these agents will strut, okay? And when we look at its properties, we'll find that there's a space in networks area of those properties. Please frob it so that it expands, and you'll notice that there are some characteristics specified here. The most important one to which I want to draw your attention is neighborhood type. We indicate here a given person, how are they connected with neighbors? And we actually have a choice here between several types of neighborhoods. Euclidean 4 neighbors or more 8 neighbors. The idea here, ladies and gentlemen, is simple. People will be in a grid, and it would be nice if we could do this with a working marker. Okay, we're down 2 to 0. Okay, here we go. And if we have a given person here, an index person, let's consider this person the center. The question is, to whom are they connected? Are they connected to the 8 individuals in not only north, south, east, and west cardinal directions, but also northeast, southwest, etc.? Or are they only connect with those in cardinal directions? Okay, that will allow us to sort of change our assumptions. But the point is, there you have neighbors. Why is it important that they have neighbors? Does anyone want to posit a guess? Based on what we've seen thus far, why is it important who their neighbor is? Yeah, they're coming in contact with them. It's to the neighbors, ladies and gentlemen, that they are going to, the neighbors who are going to be exposed. If I'm infected, it is to my neighbors that I expose myself, that are exposed by me to infection. And you'll notice that when they come into contact, they send this message to a random neighbor. Okay, so thus far we've been looking at what would be called modeling. This is modeling. We're describing a situation that seems on the face of it not too complicated, and we're systematically describing it in a precise way. Precise in the sense that the assumptions are firmly stated about all the elements. We're not waving our hands about how people recover. We say they recover according to a certain defined hazard rate, which is based on values that are specified by the model. We specify that when they come into contact with others, it's 2 people who are in the north, south, east, west, northeast, southwest, etc. of them. We have a sort of theory of personhood that's precisely defined, and that's useful, it turns out. Being able to put that in the clear light of day, let other people scrutinize it, judge it, help make suggestions to make it more realistic for certain concepts. You get somewhere by modeling alone. there's a lot you can gain from just building a model sometimes. But this class is not just about modeling. It's not just about characterizing things in the world in a mathematical way, in a mathematically precise way, as useful as that is. This class, ladies and gentlemen, is about simulation. And one of the big motivations for building a model that's precise is we can simulate it. We can take all these assumptions which we've characterized and add them together and see what the results are. And it may seem pleasant. Why would we want to do that? I mean, it's fairly obvious how this works. It's obvious how any one piece of it works if you focus on that in isolation. How they all combine, how the size of the space and to whom people are connected, and two people have contact, and the durations involved have actually very complex implications. Complex in a mathematical sense. They can give rise to surprises. So in this case, it's a very, very simple example, and the resulting behavior is comparatively simple, but at the same time, it can elicit real difficulties thinking it through in our head alone. We use the simulation to elucidate, to help us understand what's the logical implication of this, over time. What's the logical implication? What sort of behavior does this lead to over time? So I'd like to run this model. This model is runnable. It can be executed in terms of saying, okay, these are my assumptions, go figure. Go tell me what the logical consequences are for the system as a whole, for the population. So I'm going to go here within the model, and I'm going to go over to this thing marked with an X. And that stands for experiment, ladies and gentlemen. And I'm going to right-click on it and choose Run. Okay? Run. This is one of several ways to run in AnyLogic. We can also do so with it up at the top. But when you run it, you should get something like this. Do you see that? Do some people see it here? Okay. You don't? You can look at someone who does. Okay, so when this comes up, there's an introductory screen that allows us to change assumptions, change how quickly we're going to run the model, etc. I would like to go and run the model up front just on its own terms. This indicates, the fact that this is depressed indicates in so-called virtual time mode. It tries to run it as quickly as possible, and I'm going to press this button to engage and tell it to run. Okay, so what are we seeing here? I'll tell you, as in the coloration by an individual, gray is recovered, susceptible is yellow, and red is infective. So what are we going to see, do you think, when we run this model? I'll tell you, I won't show you, but I'll tell you one person starts infective in the lower part. What do we expect to see? What would we expect to see? Yeah, it'll spread out. And why will it spread?
Because it spreads to the neighbors.
Yeah, so it spreads from one person to the neighbors of that person, and before that person recovers, it may have infected several neighbors, and it can spread from them and so on. Good. So let's take a look at this and consider it more closely. Okay. So I'd like to go and I would like to ask you to go and change these settings to not run it at a fixed time, but I'd like to go up here and pick this, and I'd like to run it for 50 time units, in this case days. Okay? Days. 50 days. How did I do that? What did I do? I went and I did run here on the experiment. So I closed the old one. I went and I did run. And I went here and said run for, and I'm going to say 50 days. And I am going to now press this button. And I'm in fact going to go switch over using that button. Okay? So here we are simulating this out. Okay? And You'll notice time is not shown here. I'm going to go change it. I thought model time was enabled, but I stand corrected. Okay, so it actually ran it for a lot more than that. Let me figure out why that is here. It should have run it out to time 50. There we go. And I am going to go here. I may need you to do this. Yes. Okay. So because of the way this is set up, I apologize. I'm going to need you to follow a little bit a more intricate process. So what I need you to do to witness what I'm witnessing is right-click here, say run, okay, and then go here, say run for 50, and then I'd like to press that button to run it for 50. You'll notice it will stop here. If you pull down this, you should be able to say model navigation. How did I get that? I pulled down this little thing and said model navigation. And I pulled it down and looked at main. So here we are 50 time units in. If we go and we scroll up here, you'll notice that we have a graph of the number of susceptible, infective, and recovered individuals over time. Okay? If I were to run this forward for, let's say, another 50 time units, how would you expect these to change? So the number of susceptibles is coming down precipitously. The number of infectious individuals is rising. If I were to run it forward for another 50 to time 100, how would I expect things to change? Anyone want to posit a guess? Will it continue to rise? Will it fall? What do you think? Speak as in one voice. How many people think it's going to continue to rise? How many think it will not continue to rise?
It will slow down.
Okay, we're gonna need to get the interactivity of this up. So I started to hear a voice though. This is great. What was that?
I think it's gonna like keep going up but slow down a little bit.
Okay. Okay, so let's try that. Let's run it for another 50 here, okay? So it's running out here. It's expanding and okay. So there was some slowdown. What's happening now? What's going on now? Yeah, okay. The number of infectious individuals, is it rising right now? No, it's no longer rising. It's declining. Why is it declining?
It's running out of people.
It's running out of people to infect, okay? It's like a wildfire that's kind of exhausted its area, and there's no longer enough people to infect. That's part of it. But what else is occurring? I heard a lone voice. What else is happening?
Recovery.
Recovery is going on. And the recovery is the process by which, so infection is the process by which people become newly infective. Okay, fair enough. Then you're not being able to infect new people, so it's going to be a smaller number. What's also happening is the number of people to recover is skyrocketing. Why is that going up? Because there's a lot of people infected to recover, okay? So we have a comparatively large number of infectives. It's no longer rising, but it's still large. And that's leading to a rise over time in the number of recovereds, because some of them are recovering. So we have these two influences that are pulling down the number of new infections, the change in the number of infected individuals, pulling it down. Both the fact that we can't affect as efficiently anymore, and there's a lot of people recovering. We'll come back to that point in a later point here. If we were to continue this to run this out, what would happen? Another 50. Okay. So what's the situation now? Is everyone infected?
No.
Most people are in fact what? recovered. Has everyone been infected?
No.
No. There's at least one lucky survivor there in the periphery. Okay. So fair enough. We've seen sort of a run of this, and in fact, if you were to run this again, you would find exactly the same scenario plot out. And it's because if you go down within this and you check in randomness, it's actually running it with what's called a fixed seed, which basically means it's running it with the same sequence of random numbers over time about who contacts whom and how quickly they recover. And it's going to be exactly the same Groundhog Day scenario every time. So what you'll want to do is change it to random seed, and you'll see a variety of small possibilities, but they're all pretty similar in terms of the overall features. But, ladies and gentlemen, I changed it to random seed, and I would urge you to do that for our next step. Next, we are going to go and we are going to create some alternative assumptions about this model. You'll notice if you go to the simulation in the properties area, where we change this to random seed, and you were to scroll up, what you will find in this area is some assumptions in the form of what we call parameters. Okay? These are specifying particular assumptions about to use in the model. The overall processes are depicted. The particulars of what to assume concerning them, like how quickly people recover, etc., are specified in these parameters. And they're specific to an experiment. They're not hard-coded in the model. They're specific to an experiment. We can specify them in experiment because they are parameters in main. Okay. Now, you'll notice these are the so-called baseline parameters. These are our sort of reference parameters. They may not be privileged, but they give us a point of reference. It's a yardstick against which we can make alternative comparisons. Okay, so what I'd like you to do is I would like to go and I would like to copy this scenario to others. Before you do that, I'd actually like you to frob one thing. If you go down further, I should have enabled, when preparing this example in properties, I should have set model navigation. This is in the window area. I should have chosen model navigation and animation setup here for choice. Excuse me, not animation setup, model time. Okay, model time and model navigation. So I'm going to enable that before I clone this. Okay, so I'm going to now copy this given experiment 3 times. Okay, so we're going to copy it for 3 alternative scenarios. Okay, so how am I going to do this? I'm going to right-click on this experiment and select copy. You can also use option click or command click or whatever it is on Macs and control C on Linux and PCs, on Windows. Okay, so I right-clicked on that. I did copy. Now, I'd like you to go up to the model as a whole, and you can do paste. And you'll notice it created a new version of the experiment. Okay? With any logic, save early, save often. Okay? You'll notice that this is got a star next to it. You'll want to save it because it indicates it changed, as may be familiar with you from Eclipse. Okay, so I'm going to click on this one called Simulation 1. And I am going to call this experiment instead. I'm going to call it Fast Recovery. Okay? This could be associated with, say, fast diagnosis. So I'm going to call it Fast Recovery. Okay? There we go. And for Fast Recovery, I would like it to be two days instead of 15. Okay? Average illness duration for Fast Recovery is 2. Having done that, I would like to go paste another experiment in. Now, for those who copied it, you might be able to just right-click here and do paste because it's still in the clipboard. It's still the thing being copied. In which case, you can call this one it is called slow recovery. Okay, slow recovery, and this one will be 50 days, 50. Okay, and we'll go with those for now. Okay, so what did I do? If anyone's having trouble following along, I right-clicked here, I did copy. I went up to the model as a whole, and I did right-clicked, I did paste. Why the model as a whole? Because it's being pasted in the model as a whole. And I then went and I renamed this. I called this fast recovery, and I changed it to 2 days of duration. And the other one I called slow recovery, and I changed that to 50. Okay, so I'd like to ask you, here's 2 alternative scenarios. What difference in behavior do you think it'll make that we're making these alternative assumptions? So suppose we say slow recovery, 50 days. People stay infected for 50 days. How's that going to affect things? Will it lead to more people being infected? Overall, cumulatively? Will it lead to a larger number of people who have ever been infected? Uncertainty or shyness? I'm not sure which. Okay. Will it lead the infection to spread faster?
Yes.
Okay, why might it spread faster?
Because people have recovered from it as quickly, so there's more carriers.
Okay. Anyone want to posit something different?
I don't think so, because the contact rate is 1 per day anyway.
Okay. So the fact that the contact rate is 1 per day, what's the implications of that?
So fast recovery means less people infected.
Okay, fewer people infected if they are engaged in fast recovery. Would slow recovery mean more people infected?
Yep.
No? Okay. How many people remained uninfected last time?
1.
Okay. So now we'd expect 0, maybe? Maybe. Would it spread faster with 50 time units to recovery? Well, let's look. I mean, we could try to think about it, and it's good to try to think about it. But let's take a look at. I mean, computers are really, really good at telling us the logical implications of things, which are very straightforward to describe and to sort of in a cut and dry way simulate. So here we go. We see the simulation here. What's the difference from before? Can anyone see a few differences? If we were to do that for that time, I'll repeat it one time so you could see it here. So we're simulating it like this versus when we did it before, the one with 15-day recovery time. What's the salient difference between these two? Do you notice? Anyone notice some differences? What's that?
Dispersed infection behind the wave.
Yeah, okay, there's with the longer recovery, there's people who stay recovered behind the wave as it goes out. We could time the wave and see how quickly it reaches the edge. I would argue that it in fact does not cross the space that much quicker. Why not? Well, it turns out that there's already a saturation effect. People are staying infected for 15 days. They almost certainly infect all the nearby people who are susceptible. If they stay infected for 50 days, there's not a lot more infection going on of those people because they're already infected. They can't be reinfected again. They're just on an ongoing basis, they're infected for a while, and so it's not going to be adding that much. More than that, the number of people infected is not that much more. Maybe that final person gets infected. What it mostly does is shift it up in terms of when those people are infected. They tend to be infected somewhat for longer periods, and therefore the numbers are higher, right? How about fast recovery? Let's simulate this. Let's try fast recovery, okay? What do you think we'll see for fast recovery?
Fewer people infected and more people susceptible.
Ah, okay. So what's gone on here? What are these things? These islands. Let's try that again. Let's try this again, okay? Well, rerun it. I could have actually done it just by saying stop and gone back to this. Why are we seeing this different picture of what comes about? Say this looks qualitatively different in terms of its results. Why? Why is this the logical result of our assumptions?
Less opportunity for infection, contact with the
Okay, so less opportunity. They're recovering fast enough that they don't always infect enough of consistently all the neighbors, and therefore there are pockets in growing numbers who remain uninfected. So that's good. I'd like to go through. So there we have a transition that's not only a matter of timing. When did they get infected? We actually see something that's quite different in terms of the ultimate outcome, which is we have a lot of susceptible still at the end. So if we were to run this and run it flat out here, you may notice that here we get something where the number of susceptibles comes down, but it's not totally drained down. It actually remains there. Okay, I'd like to make one final change to this. One final change that will lead to a change in dynamics. This change is not going to be merely one of degree. We're going to qualitatively change an aspect of the dynamic hypothesis, sort of the theory we're capturing in the model about how infection works. We're going to posit here that you can lose immunity over time. Okay? That immunity is not forever, that it's not permanent, but in fact, you can lose your immune status and become susceptible again. So what do we need to add to this theory as it's depicted here in order to capture that sort of added twist to things? What do we need to put into place? Okay, transition. Whence does that transition need to come? Where does it come from?
From recovery to susceptible.
Okay, recovery to susceptible. Okay, so let's put this into place, right? In order to do this, we need to go view and call up the palette. Okay, now when we call up the palette, you'll find that the palette, like a good painter's palette, has lots of different components in it. I'd like to go down to the agent one, and you'll notice there's a transition. The agent looks like it's a Da Vincian emblem in red with an outstretched person, a person with outstretched arms. So I'd like to go down to agent. You could alternatively go to state chart if you wanted to. And I'd like to drag out transition so it goes from recovered to susceptible here, okay? So how did I do that? You'll notice it needs to be green on both sides. How did I do that? I went to agent in the palette, this red one. I dragged in transition here. I hitched it up so it comes from here. Notice it's green. Green is good. Green is the color. State charts of the game. And it needs to go to susceptible with green as well. This looks ugly right now, so I'm going to engage in prettification, if you don't object. Hearing no objections, I'm going to double click here and drag out here like this, okay? And and it looks less hideous even by my engineer's eyes. Okay, and here we're going to associate this transition with a rate transition. Okay, it's going to be a rate transition. I'm going to call this transition waning of, or call it waning immunity, meaning my immunity is decreasing over time. It's a rate transition, and the rate, ladies and gentlemen, is 1.0 divided by 150.0. In other words, it'll be 150 days on average you spend in this recovered state. We'll talk about where this came from later, but it turns out if you have a rate, a hazard rate of X, your mean time in that state from whence you come is, if there's no other transition out, 1 over X. Okay, so if I have a rate transition with a value of 1 over 150, the actual amount of time I spend in that state on average is 150 time units. 1 divided by 150, okay, which is 150. Okay, so I've just put this transition in. I've posited that once one becomes recovered, you have a small chance each day of recovering or going back to susceptible, and on average you'll spend 150 time units in the recovered state before losing immunity. What do you think the implications of this are over time? What's the cumulative implications of this process we specified? Once we've added this transition, what do we see? What would we expect to see?
If you run an experiment for long enough, all the people won't be recovered.
Okay, not all the people will be recovered. Some will be susceptible. Okay, good. So I like that. Other implications. We have people losing their recovered status. What else could happen? Okay, there'll be a wave of infection. Why a wave? We already saw a wave of sorts, but what would this one lead to? We saw a wave spreading out, right? It was sort of a repeating of infection. Okay, I like these ideas, but look, computers are very good at doing dumb things repeatedly, like figuring out how to iterate a model. So let's have the computer tell us here. It's good to challenge yourself, but here we go. Okay, so now we have a situation where we have, this is for the case of the sort of normal delays. Okay, we see a rather different situation. What's going on here? What's going on here? Do we see big waves right now? Are there big waves? What do we see? This is sort of with the normal delays. We see sort of scattered little bits of infection. Okay, let's try for the slow recovery. What will we see here? If we have slow recovery with this, what would we expect to see?
Never-ending infection.
Okay. So let's try this. Okay, so it's spreading out here. Why is this a logical implication of what we've just said? Why never-ending infections? What? Sorry? Uh-huh.
More people are becoming susceptible.
Yeah, so more people are becoming susceptible. What happens once they become susceptible? Remember, it's long recovery. What does that mean? People stay what longer? Infected longer. So if I'm someone who's recently become susceptible, there's people around me who can do what to me? Infect me, right? There's enough people around me who have stayed infective. They may infect me. Okay, whoops. Okay, now let's take a look at the case of fast recovery here. Okay, So what would we expect to see for fast recovery? So that, remember what we saw before. Ah. So what's going on there? Why is everyone susceptible? It was one of the first things mentioned in positing what might come about. Why is everyone susceptible? Yeah, a lot of them were exposed at some point. They got infected, they got recovered, and they became susceptible again. And the infection essentially died out. It died out after spending some time in there. Let's run that again. Okay. So here we go. Here we're going to have the infection spread out, and it kind of goes through the population, but it dies out because people are recovering fast enough that at some point the last spark dies, and they end up not having anyone to infect them further, right? I would invite you, we don't have time to go through it right now, but I would invite you to try one more scenario where we have a recovery time